who's going to tell us about newly discovered satellites.
Okay, thanks. Okay, so most of my day job is simulating the whole universe and the dark side, but today I'm going to give an almost entirely observational talk on newly discovered satellites, both within the Milky Way, primarily focused on results from the DES collaboration, half of them announced earlier this year, and then the other half from a paper that appeared on the archive on Sunday night. And then I'll spend the last few minutes of my talk talking about satellites beyond the Milky Way in Milky Way analogs. This is work in progress with the SAGA collaboration. So let me first introduce the Dark Energy Survey. I've been working on this project now for more than 10 years, and we now actually have data, so it's quite exciting. So this was a new camera built for the Blanco telescope. It's doing a 5-year survey, a little more than 500 nights, over 5,000 square degrees, roughly to 24th magnitude in GRIZ. So it's got a big field of view. It can do lots of awesome stuff, and the main target is to do dark energy with several different methods. But there are other things you can do with this with this telescope. So we've just completed the second year of data, and actually just started the third year of data. So this is just showing the number of tilings that exist in the DES footprint, which has this very strange shape, which was basically primarily to overlap with some spectroscopy here from Sloan, and then to overlap with the SPT survey here in the south. Okay, so the exciting thing that we've now done with these first 2 years of data is we've detected 17 new dwarf satellite candidates in the Milky Way. So this picture here shows the footprint now, looking at the area covered by the Sloan survey, which is up here, and the area outlined in red covered by the Dark Energy Survey. And this figure shows all of now the known satellites, and some of them satellite candidates in the whole Milky Way. So there were sort of 11 classical satellites. There were 15 satellites discovered by the Sloan Digital Sky Survey. Actually now 16. There was one discovered very recently with a reanalysis of Sloan data. A handful of other satellites also discovered in the last year from other surveys, and then these new satellites from DES. So this is now almost our entire footprint. So the Bechtold et al. Paper that was published on the archive in March was about 1,800 square degrees. The new data set is about 5,000 square degrees. So it's not quite, but almost the whole footprint. But it's not yet to full depth. So this is just the discovery timeline here of all of the satellites, right? This jump here was due to the Sloan survey. And then this is all of the satellites discovered in 2015 with this kind of timeline. This was sort of the DES year 1 data, and then there were this sort of smattering of objects detected from other surveys in the intervening months, and then this is the paper on the archive this week. So 17 using the DES survey itself, actually 2 others using DECAM with other surveys, and then the other 3 are from Pan-STARRS. Okay, so these are the 17 satellites. Here's our footprint. And these objects are the objects that were detected by DES. The circles are the year 1, and the triangles are the year 2 candidates. This right here is the LMC. This is kind of the edge of the SMC right here. So you'll notice something very interesting here, which I'll comment on a little bit further later, which is that there are a lot more satellites down here than there are up here. So that's interesting fact, but anyways, lots of interesting objects here. So these are just some basic properties of the objects. They're fairly similar to the objects detected by the ultrafaints detected by Sloan, but we are detecting objects that are lower surface brightness than any of the objects that were known before. So 2 of the objects are at about 30 magnitudes per square arc second. And at a given magnitude, we are detecting objects that are further away, as we expected to, given that the survey is deeper, but that's a really nice confirmation. So here's a summary of all of the satellites. This is a table from the recent paper. These are the year 2 ones, and these are the year 1 satellites. So 3 of these objects actually have now been spectroscopically confirmed. The other ones sort of await confirmation. Let me just mention, most of these new objects, clearly, there's still some ambiguity about how many of them are satellite galaxies, if any of them are globular clusters, but many of them are clearly over here where they really seem to look like the locus of satellite galaxies. So I would guess that, most, but not all of these 17 are galaxies. So they have properties that, are similar to the Sloan ultrafaints. This one, I think, would be the least luminous galaxy known yet, if confirmed. But this one is in a kind of a patchy area of our survey data, so its properties are less well known. There's some interesting things that, a handful of these are quite nearby. This object here, Reticulum 2, this was from the year 1 data. This received a lot of interest here because it's a good candidate for looking at with Fermi. We have another new satellite, Tucana 3, which is also very nearby. So it's another good thing to look at with Fermi. Okay, so I'll just say a few words about how these were found. In the year 2 footprint, we used a combination of search strategies, and this work was primarily led by Keith Bechtold and Alex Strelica-Wagner. And it was using a new catalog put together, basically quick and dirty catalog of the year 2 data, not going to work for weak lensing, but can be used for these search strategies. So people actually looked at things by eye. There was a simple binning strategy, which is very similar to how things were done in Sloan. And then a very nice new method that Keith and Alex have developed, actually based on work that we had done earlier to find galaxy clusters. It's the same kind of basic idea of a matched filter technique for the stars, where you basically have membership probabilities for every star, and you have a likelihood for every star, and you basically go through and you look for seeds, and then you characterize this. So I'm going through this part pretty quickly, but feel free to ask me or read the paper for details. So you're basically looking for a population of stars which is consistent with a metal poor old population, and you search through using different distances and to identify these satellites. So one of the really nice things about this method, it does actually appear to allow us to push the data a little bit further, but it also gives us probabilities that every star is a member of that object. And we were able to test these with this object Reticulum 2 in the spring. So this just shows what this galaxy looks like on the sky. As usual, you can't really see it. But we have for every star then a probability that it is a member. And this was then confirmed by spectroscopic follow-up. This is work led by Josh Simon. So this guy really is very clearly a dark matter-dominated galaxy. Here's its velocity. It has a velocity dispersion of about 3.3. Mass gives you a mass-to-light ratio of 470. Okay, so let me say a few more words about where these things are on the sky. So this cool image shows us, these are some of the 14 of the 17 satellites and where they actually are on the sky compared to the Magellanic Clouds. This is the telescope they were observed with. Okay, so as I mentioned, 15 of the 17 DES candidates are in the southern half of the sky. So you can just ask the really simple question, are these observations consistent with an isotropic distribution? And this is the actual distribution of these galaxies in declination. This is what you would expect from an isotropic distribution. So I think very clearly the answer is no. The second question is, can you explain the isotropy with a very simple model where you have an isotropic background in the Milky Way, and then you have an association of objects with the LMC and the SMC? And the answer to that appears to be yes. So this modeling work was done by Yao, who you just heard from earlier. This was just done in the last few weeks. So this is a very simple model. You should just take it as an example of what might be going on. It's certainly not what's happening in detail. But the model here is an isotropic Milky Way background, and then a population of satellites that are spatially associated with the LMC and the SMC. And so within the context of this model, you can then ask, what do you get using the DES data alone and the DES data combined with the Sloan data? So we have then a constraint on the total number of satellites in the Milky Way as a whole, and then the fraction of those that are associated with the Magellanic Clouds. So this assumes that, you know, the number that we see associated with the Magellanic Clouds in the footprint that we've seen, you know, would also be seen on the other side. So that's, you know, something that we definitely want to test. It's not obvious that that has to be the case. But an interesting thing is that the DES data alone, as we sort of saw in the previous plot, you know, do show that at least in the context of this model, you do have something that's clearly associated with the Magellanic Clouds. The constraints get a bit tighter if you combine the data with the Sloan data here. So this 50% detection ratio, I should have said earlier, that's roughly what we think. So about half of the DES satellites would have been detected at Sloan depth. So that's done by actually, you know, detailed completeness of taking those satellites, putting them in sort of Sloan depth imaging and seeing whether you would detect them. So in this model, we predict of order 100 satellites to the depth of the DES year 2 data. So that doesn't mean that's the total number of satellites in the Milky Way. There should be more, you know, that we would expect to find deeper. Okay, so just summarizing this part of the talk, what do we expect in the next few years? So somewhere between 50 and 80% of the sky is now observed to Sloan depth. Why did I say 50 to 80? 50 is assuming basically just Sloan plus DES. 80% is assuming that the Pan-STARRS survey actually has observed to Sloan depth. Since they have not actually published depth maps or completeness, I just don't know how deep their search is. So there's a lot of imaging coming. This is all sort of the pre-LSST imaging that's coming in the coming years. So we'll have 3 more years of DES data. We won't have a lot more area, but we should be able to find galaxies deeper and farther away. There's a set of imaging surveys that are being done as a precursor to the DESI spectroscopic survey. That's about 14,000 square degrees, about a magnitude deeper than, sorry, that should have said a magnitude deeper than Sloan. It's not, definitely not a magnitude deeper than DES. So that overlaps with Sloan and then is a bit larger than Sloan. And then there's a bunch of other surveys happening now and in the next couple of years. I think there's a really interesting question. As we basically push the data any deeper than the search we've done now on DES, galaxies start to dominate over stars. And so how deep we can push this is really, the big question is how well we can do the star-galaxy separation. It's going to be a lot more observations coming. I think, you know, our team and many other teams will be going after these galaxies spectroscopically this fall and in the near future. And there will be a Fermi analysis of these dwarfs coming in a couple of weeks. And then I'll just say, sort of on the theoretical side, there's just a huge number of questions, I think, that these data bring to mind. So are the numbers and the radial distribution fully consistent with the lambda CDM predictions? As we've been talking about a lot at this meeting, what are the lambda CDM predictions in the presence of baryons? What do the star formation histories look like for all of the satellites? And, you know, what can we learn from actually measuring those and comparing them to simulated data? How many satellites of satellites are there? And do they look any different from objects at the same luminosity? Can we actually see, for example, pre-processing of those objects that came in, for example, with the Magellanic Clouds? I think there's a lot we can potentially learn about the Magellanic system itself. And, you know, Alice Deason wrote a nice paper a few months ago saying that, you know, if you really do have a lot of satellites, that also gives you a constraint on when the LMC came in. And then there's been these claims, you know, we presented this one possible explanation for these things. This plane of satellites that people have talked about also goes straight through the DES footprint. So some of these, you know, you sort of would have naturally expected some of these to lie on the plane, although the ones that are closer to the SMC look a bit further from the plane. So I think the evidence for this actually goes down a little bit with these new discoveries. And one of the reasons we did this fairly simplified model is that in order to really fully interpret these, you really need a better understanding of your completeness of these surveys as a function of luminosity and size, and that's stuff we're working on now with the DES data. And we also really need a more comprehensive modeling approach, and that's, Yao and I are particularly working on that now. So now let me talk about how do we put the observations of the Milky Way into context of the broader cosmological model. So you heard from Yao and others about how we have a diversity of halo properties, and that predicts a diversity of subhalo properties. So what does that imply for the diversity of satellite properties? So I'm interested in not just simulating this, but seeing whether we can say something about the properties of satellites that are like the Milky Way, but different from the Milky Way. So this is a project that Marla Jiha and several others and I have been working on now for a couple of years. The basic idea is to identify host galaxies that look like the Milky Way. So basically isolated L-star galaxies. These are just, at the moment, galaxies selected from Sloan imaging. And they're relatively nearby, so about 20 to 45 megaparsecs. And these are just an example of 9 of the galaxies that we've looked for their satellites of so far. So the basic idea, right, here's an example. This is one of our galaxies. This is the virial radius of this galaxy, so it's actually a pretty big piece of sky. So 300 kpc at the distances that we're doing this survey is about a square degree. So that's convenient for spectroscopic follow-up. But there are about 5,000, roughly, objects per host within that radius, and we're looking for something like 1 to 10 of them. Okay, so the first thing we have to do is to figure out which ones of them might possibly be satellites. We're aiming to go to a little bit deeper than Fornax, depending on the distance of the host to minus 12 or minus 10 in R-band magnitude. Okay, so in the first phase of this project, we really wanted to make sure that when we chose which one of these were likely to be satellites, we were complete. And so we really just went for getting lots of spectra to make sure, because photo-Z's in this regime are just not very good. There's just, there's so little data in this regime that we thought we really needed a lot of spectra. So we actually have more than 13,000 spectra that we've taken so far. A handful of those are at low redshift, but it has a broad distribution. We made some basic color cuts to limit this, and then we're doing a simulated sample in parallel. Okay, so far we've detected 17 satellites. This was just a coincidence I noticed this week as I was preparing this talk, that we have 17 satellites in SAGA and in DES. Interestingly enough, the first host that we really went complete on seemed to have an anomalous number of satellites. So this particular host actually has 9 satellites that we've identified. One of them was fairly bright. This one had a spectra from Sloan. I think this one might have had a spectra already, and the others we got spectra for. So very interesting that this one has a lot of has a large number of satellites. This is, again, this faintest one is just a little bit dimmer than Fornax. This one is actually also quite interesting because all of the satellites around this host appear to have star formation. So they all have emission lines, all 9 of them. There is some trend with radius, so they have stronger equivalent widths in the outskirts than they do in the inner region. This is the tiniest one. So this is the really little one. It's anyway, so very interesting. So this is still. There's no Andromeda. But we don't think that Andromeda has a big impact on this.
Well, it's a little teeny tiny group, right? So you're not in the same kind of environment.
Yeah, so we're looking carefully at these environmental trends, but I don't think that Andromeda has a big effect. I mean, James also worked on this and showed a similar thing, that Andromeda should not have a big effect on the satellite population. Okay, so I'm almost out of time, so I'll just summarize also with the observational and theoretical outlook of this. So we have so far with this project, we have 7 host halos that have more than 70% completeness for likely satellites. One of these hosts has 9 satellites, and most others have like 1 to 3. But we're still, don't take this too seriously because we're still really understanding our completeness. That's something that's in progress. We actually do already have high-resolution spectroscopic follow-up with keck of, I think, 5 or 6 of these satellites that allow us to get velocity dispersions for them. So that's sort of a key element of this. And we now think that using these the sort of data from the pilot project, that we now have a search strategy that basically allows us to get all of the satellites with one pointing on typical multi-object spectrographs. So that will actually allow us to get up our numbers quite a bit more. So I'm very optimistic about this. So what are we trying to do with this? I think we heard from Frank and Yao earlier that we now have a much better understanding of what the subhalo distribution looks like in CDM, at least without baryons. And we're continuing to study that with a SAGA targeted simulation suite. But we really need a fuller understanding of how satellites are connected to subhalos. So what's the scatter in the subhalo satellite connection? How do the satellites depend on the galaxy properties, on the host galaxy properties? And what do the baryons do, both to the subhalo properties and to the subhalo survival? So I think these are some of the key questions that we'll face in the coming years. So I'll just finish here, and I think these 2 sets of data are really going to be very exciting to give us a full understanding of the Milky Way satellite population in its full cosmological context. Thanks.
For hydrogen, neutral hydrogen, how many do you expect to see?
Yeah.
With the star forming?
No, that's a great question. I think most of the SAGA satellites can be targeted, and so far, the very few that we have don't have H1, but that's something that I think is very, very interesting to look at in more detail, especially for these star forming ones.
Don't have in the sense that you haven't looked, or don't have in the sense that you've looked and not?
At the limits of the things where we've looked, but the data is not deep enough to really say very conclusively. Yeah.
So I was wondering what you make of this system that you found. There's how many satellites does it have, and they're all brighter than Fornax?
Yeah, it has 9 satellites. 8 of them are brighter than Fornax.
Do you think that that's just like a crazy 9 sigma thing, or because that's so different than what we would think. You'd have to I don't know.
Yeah, so this galaxy might be a little bit brighter than the Milky Way, and it does appear also to have more bright satellites. So maybe it is an anomalously. I don't think it's 9 sigma. Yeah.
I was trying to be a little extreme.
Yeah, I don't think it's anywhere near 9 sigma.
I would just add, so there's this plot that Sean showed that's like Coral's Point and then all the dwarfs. Well, Fornax sits in the middle. So if for some reason it's really the Fornax scale where things can form stars, and then it's only below that, I don't know.
I think it's a great question, and I feel like we need a more comprehensive modeling approach to really answer it, and that's what we're working on now.
One last question while the next speaker connects. Frank.
What are you doing with 13,500 spectra minus 17?
I'm open to ideas.
Good. How did you do the tech?
We're brilliant.